All right, this tutorial is to show you how to choose the right model settings for when you run Maxent. The first place to start is to go to my website. And download the files needed for this tutorial. So this is the one, how to decide which setting to use when running Maxent. This tutorial will also show you how to make a bias file if you need one. But before we download the files needed for this tutorial, I want to draw your attention to the species distribution modeling flowchart. There's two different ways that you can run species distribution modeling. One is that you can filter your occurrence points so that no 2 points are close to each other. That's one way of dealing with the problem of bias in the distribution of your occurrence points. The other option is to not filter your occurrence points and make something called a bias file. I am finding that this approach of making a bias file is becoming more and more preferred. What I'm going to show you today is how to run a function called ENMEval within R that will let you see what model settings you need to use when you run Maxent for your data. And I'm going to provide you with two different versions of the R script. One that will create a bias file and provide that bias file to you for other purposes. Another version of that R script which will not create a bias file and that will not use a bias file. The first thing you have to decide is, based upon your particular project, if you are using a bias file or not. And that will determine which of the two R scripts that you'll use. So refer to this flow chart. And I also want to point out that if you are going to be using a bias file, you're going to need to make sure that you include it in your ENMEval code. So you're going to want to make sure you use the right script. And when you eventually run Maxent, be sure to use the bias file in your run of Maxent. If you're not using a bias file, you don't have to worry about that. All right, now we're going to download the files needed for this tutorial. And we'll do that by clicking here on the triangle next to the word download in the right-hand corner. We're going to click on direct download. All right, I'm going to go click on File Explorer. I'm going to navigate to my Downloads folder. I'm going to double click on my Downloads folder to unzip it. Well, and right now we're looking inside of the compressed directory. I'm going to hit Control-N to open up another copy of File Explorer. And then I'm going to go to my desktop, and I'm going to click this button here, new folder, to create a new folder on my desktop that I'm going to call ENMEval. I'm going to open up that folder. It's empty. I'm going to go inside this ENMEval folder. I'm going to take all the contents, highlight them all, and move all of the contents into this ENMEval folder on my desktop. Okay. Next, I'm going to come down here to the search window, and I'm going to look for RStudio. I'm going to double click on it. And I'm going to come up here and go to File, Open File. I'm going to go navigate to that folder on my desktop called ENMEval. And for the purposes of today's tutorial, I'm going to show you how to run ENMEval where a bias file is created and used in the evaluation process. So we're going to use this version of the script. But however, if you did not want to use a bias file, you would use this other version of the script, which is very similar, except that it doesn't create a bias file and it doesn't use a bias file in the analysis. All right. Next thing, now that we have the script open, is we need to set our working directory. So session, set working directory, choose directory. And I'm going to set my working directory to the ENMEvaluate folder on my desktop. Be careful that you don't have any subfolders. If you have your data in a subfolder of ENMEvaluate, for instance, I see a common mistake where there'll be a subfolder with the same name called ENMEvaluate. Make sure you navigate to that subfolder as your working directory. But in my case, it's just this directory called ENMEvaluate, which is on my desktop. All right. Next, I'm going to install some R packages. Installing RJava can be quite tricky. And if you are experiencing problems installing RJava, you're going to want to follow the instructions that I have written out here as a link. In fact, if you're having trouble installing ENMEval, it's going to be for the same reason. It's going to be because of problems installing RJava, as RJava is a dependency of ENMEval. And so again, even if it's just having problems with ENMEval, you're going to want to come down here and put this link into a browser window without the hash symbols, so that you can read more about troubleshooting installing the RJava package. Anytime you see these hash marks, it means that this is a line of code that's not going to be read by RStudio. So this is where you can put notes that are not going to be read by the computers, by the RStudio software when you run your code. All right, so first we're going to install the package RJava. The reason I have it hashed out is that you only need to install packages the very first time that you ever use those packages. From here on out, after we've installed these packages on our machine, we won't ever have to install them again. So to install it, we're going to just highlight the command without the hash symbol and click on Run. Okay. Now we're going to highlight and install the ENMEval package. Again, do not highlight the hash symbol. Click on Run. Okay. Now when you do this on your own, you'll find that it could take a lot longer to install these packages than it took for me. Don't be surprised by that. Next, we're going to install this package called raster. Again, don't highlight the hash symbol, but highlight everything else and click Run. Once you've done this on your machine within your user account once, you never have to install these packages again. They're always there available to you. The other lines of code that are not hashed out, those are things you're going to have to run every time you're coming, turning on your machine or using it for the first time that day. All right, now we're going to load those packages that we've installed into R. We're going to highlight them, click on Run. Okay, and they're all loaded. Next, this is a little unusual. There's a R package called Dismo, and Dismo is a dependency of the ENMEval package. So Dismo was also loaded right now when we were loading all of our libraries and installing all of our libraries. We need to put the Maxent software within a special folder that can be accessed by the Dismo package. So actually today, as a part of this tutorial, you're going to be running Maxent. You're going to be running not the full version of Maxent with all of the features, but a slimmed down version of Maxent that will be running in the background so that we can find the right model settings to use for Maxent. But in order to do that, we have to put that Maxent into a specific location where this Dismo package will be able to access it. So here's what we'll do. We're going to go open up your browser of choice, in my case Google Chrome. I'm going to Google Maxent software. And here's the link we want, biodiversityinformatics.americanmuseum.ofnaturalhistory.org, etc. Click there. And if we scroll down on the page, I'm going to click this button that says, I prefer to download without providing this information. And I'm going to click on Download Maxent. Okay. Once it's finished downloading, I'm going to open up File Explorer again. And go to my Downloads folder. I'm going to double click on maxent.zip to look inside of the zip directory. Remember, we have to drag these files out of the zip directory in order for them to be uncompressed. Never try to run files from within a zip directory. But we're actually not going to be running these files directly. We're going to be putting them in a specific folder accessible to the Dismo package in R. Let's go back to RStudio. We need to run this line of code here. This tells us the location where we need to move the Maxent files. So I'm going to open up File Explorer. I'm going to hit Control-N to open up another copy of the File Explorer window. And this copy, I'm going to navigate to this directory path you see here. C:, users, Josh, documents, R. Again, I'm just following the path that's written down here at the bottom. Win library, 3.5. There's the Dismo package. We're getting close. And there's Java. Now, in this case, I already have the files in there, but we're going to pretend that they're not. I would highlight them from within the compressed folder in Downloads, and I would drag those files over here into the Java directory that's accessible by Dismo. And there you have it. All right, next, I'm going to go back to the ENMEval folder on my desktop and describe a little bit more about the data. Here are the environmental layers. Now, these environmental layers are taken from a site called WorldClimb. And these are environmental layers that are available for download that give climatic information covering the entire world at various different grain sizes that you can see. And in our data, the WorldClimb environmental layers are coded as Bio 1, Bio 2, Bio 3. But if you look here, you can see what those environmental variables are really measuring. So Bio 1 is average annual temperature, Bio 6 is minimum temperature of the coldest month, etc. Notice that these are all continuous variables. So annual mean temperature can take on any number. But when you're using Maxent, you can also use what are called categorical variables. So I have added on, which I've made up. These are not real. This is just for the purposes of the tutorial, 2 categorical variables to use as well. And I'm calling them biocategorical variable 1 and biocategorical variable 2. Biocateg 1 and biocateg 2. A categorical variable means that rather than what's being measured being a quantity, it's measuring something qualitative. So for instance, let's say that biocategory 1 had to do with soil type. So I could have, so a particular grid cell could be soil type 4, or it could be soil type 17, or it could be soil type 1, where these are just arbitrary names for different types of soils. There's no sense in which soil type 1, where soil type 2 is twice that of soil type 1. That's not what is meant. It's just 1 and 2 and 17 and 3. Those are just the names of these different qualitative categories of soil. So that would be a categorical variable. And I've added a couple in here so that you can see, if you were to have categorical variables in your own data, how you would treat them when running ENMEval. Down here we have our occurrences in a file called occ.csv. This file should be in the Microsoft Excel separated values file format. And you should probably name this file occ.csv. If you don't want to name the file occ.csv, you'd need to change something in the R script. It's easiest just to name it occ.csv. Let's open this file and take a look at it. The file has 3 columns, and notice that in line 1 we have the column headers species, longitude, and latitude. You will want your species headers to look exactly like mine with your own data, and you will want to pay attention to capitalization, or in this case the lack thereof. You'll want to have species all lowercase, longitude all lowercase, latitude all lowercase. In this column here you will put your the name of your species, and you don't want to use the full real name. You don't want to use something long like that. Just something short, only one word, that it's a little note to you to help you remember what species this was. And then in this column here, you'll put your longitude data, and here you'd put your latitude data for each of those points. And you want your occurrence points to be in the same projection and datum as your environmental layers. So know your data, make sure that those things match ahead of time. And for the purposes of this tutorial, they do. And that's information that's not going to be in these files. That's information that you'll have to know from the way that you process these files. But everything matches, just be aware of that. The data here for this example we're doing today is data that's publicly available through the R Development Core team. I don't know the exact authors, but it's a series of occurrence points for a species of sloth that lives in South America. And our environmental variables, our environmental layers are environmental layers of of these climate variables covering South America. So I just wanted to give you that background about the data. And now we're going to import our environmental layers into R and turn them into R objects. So if you're doing this with your own data, you're going to want to change the names of these files to reflect the names of the files that you are actually importing into R as raster objects. And that's what would go in quotation marks here. Over here on this side, you would put the name of the R object that you want to be created when you import that environmental layer. And the way to do it, to keep it nice and simple, if your environmental layer was called bio1.asc, that's what you'd put in here in quotes. And then here for the name of the R object, just call it bio1 without the .asc. And then so on and so forth like that, but for bio5, on and on. But in this case, because in this example where you actually are using these particular environmental layers as already written, so I'm just going to highlight this block of code and click on Run. Next, we have to do something called stacking the rasters. This is a very common operation that you have to do whenever you're working with raster files in R. And this means taking all of the raster R objects and putting them together into one stacked R object that contains all of those rasters together in a single object. And so if you're doing this on your own data, you'll keep everything the same as you see here, except within these parentheses, you'll replace the names of these R objects with the names of your actual R objects from here. Notice that you don't put the .asc, just the name of the R objects. Notice that you don't put any quotation marks because we're referencing the R objects themselves. But you'd replace what's in here with the names of your actual raster R objects. All right, so I'm going to highlight this because in this case, this is the names of our raster objects. I'm going to stack them together, and we're stacking them together into a single stacked R object called ENV. All right. The next thing we're going to do is we're going to look at the stacked R object. So I'm going to highlight this line of code here, and I'm going to click on Run. Here's the important thing I want you to notice. At the bottom of your screen, I have it highlighted in blue, and you can see the cursor. I want you to notice the order in which the raster objects were stacked. Bio 1 is first, then Bio 5, then Bio 6, etc. The reason for this is if you have categorical variables in your data set, you're going to want to look at your ENV stacked raster, and you're going to want to see which in the list are the categorical variables. So in this case, our categorical variables are biocateg 1 and biocateg 2, and their positions are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 in the list. So you're going to want to make a note of that for later. All right, next we're going to read in our occurrence points. Highlight that line of code there. Click Run. All right. And now we're going to make our bias file. This part of code won't be in the other version of the R script if you're not needing a bias file. But if you're needing a bias file, here's how you make it. The first thing we're going to do is take our occurrence points and rasterize them. This means that we're going to take a grid cell. We're going to take a raster image of our entire spatial extent with grid cells of the same size as our environmental layers, which are in the form of rasters. And wherever there's an occurrence point for our sloth, that grid cell is going to be marked. So let's go ahead and do that. And now let's have a look at the rasterized version of our occurrence points. It's not really that important, the mechanics of making the bias file, but I'm still going to go ahead and show you so that you know. So we're going to highlight here and look at our rasterized occurrence points. We haven't made the bias file yet, but this right here is an actual map where on the x-axis here these are your longitude coordinates, on the y-axis here are your latitude coordinates, and each one of these little squares is a little grid cell within which that's been colored yellowish because in that grid cell the sloth species was found. And this is in South America. All right, now we're going to go ahead and actually make that bias file based upon the presences of our sloth. It's going to apply something called a kernel density function of where our occurrence points are, assuming that the places where our occurrence points are the places that are the easiest to sample, and therefore that's why we have more occurrence points from those locations, because they were easier to get to. All right, we're going to make the bias file. Right now, I'm going to run this line of code here, so just make sure you highlight without the hash mark to actually run it. Now you're going to see a bias file based upon the occurrence points. So there you go. And what this bias file means is that our background points, in other words our pseudo absences, will be selected preferentially from areas of the highest density in this kernel density function of where our points are mostly located. And remember, in this color scheme, dark green is the densest. So our pseudo absence points are preferentially going to be selected from within here and these areas of highest density of our presence points, so that our pseudo absence points will be near our presence points. All right, now we're going to run this line of code here, and we're going to save out our bias file to a file in our working directory so that we have that bias file to use later for whatever purposes we would like. All right, now we are going to run this line of code here. This line of code is going to show us how many potential background points there are available in our data set. And so what this is going to tell us is how many places there are on the landscape, how many unique grid cells there are on the landscape where where pseudo absences, or in other words background points, could be selected from. So I ran that line of code, and the answer is 9,775. Usually we would want to select 10,000 random background points, but the number of background points that we select should be far less than the total number of grid cells available in our spatial extent. In this case, the number of grid cells available in our spatial extent is 9,775. So we don't have a number of background points to choose from that's equal to 10,000. So we want to choose something that's far smaller than 9,775 as our number of background points. So for the purposes of this tutorial, we're going to have to use 5,000 background points. But if this number here of the number of available grid cells to sample from was far in excess of 10,000, then we would want to change this line of code here from 5,000 background points. We would want to change this to 10,000 because 10,000 would be more ideal. All right, now we're going to generate our background points that will be used by ENMEvalUate as a part of running Maxent and finding the best settings for Maxent. And these background points are going to be sampled from are going to be chosen as informed by our bias file. Here we go. All right, now we've got our background points, and now we are ready to run the ENMEvalUate function to actually see which settings in Maxent will be best given this data. I want to take a minute, though, to describe the different arguments here that are a part of this ENMEvalUate function. This refers to your occurrence points. So let me get back to that for 1 second. If your occurrences have a different name, you're going to want to change it here and here. But assuming that that's the name of your occurrences, here's your occurrences object. This is your environmental layers. These two arguments here refer to the method that's used by ENMEvalUate to make replication. And the method that I have for the purposes of this tutorial is the random k-fold cross-validation method that uses 10 cross-validation folds. Another method that you could use instead would be something called the block method. And in fact, the block method under a lot of circumstances may be preferred. If you were using the block method, you would replace the lines that say method random k-fold, method is equal to random k-fold and k-fold is equal to 10. So you replace these two things here with something that simply says method equal to block. All right. This here is an argument showing you about your categorical variables. So in this case, the categorical variables were numbers 9 and 10 in that list. Remember I told you to look over that list and to make a note of which ones are the categorical variables in that list. In this case, it was numbers 9 and 10 in that list of stacked rasters. But if your categorical variables were numbers 2 and 7 in that list, then this argument you would want to change it to read categoricals equals C parentheses, I believe I said 2 and 7. 2, 7, if that's where they were in the list. If you only had one categorical variable and it was at position 4 in the list, you would want to change this to read categoricals equals C parentheses 4. If you had no categorical variables in your list of environmental layers, you would want to remove this argument about categoricals from the ENMEvalUate script. All right, I'm going to go ahead and run it. and it's going to take a while to run. And you see a progress bar down here. We're at 2%. Now we're at 4%. It's going to take about 20 minutes to run. So I am going to pause my recording here and get back to you when it's finished. All right, and the analysis is completed now. Don't worry about if you get errors when it's running. They could be bad. In this case, the errors that I received are benign. And we can see that it took 18 minutes to run. So now we're going to actually skip this line of code here. This is if we wanted to look at the results within R. But what we're going to do is we're going to write the results out to a file. And then we're going to open up the file and look at the results. Okay. Come here to our File Explorer. Make sure that we're in our working directory, and we're going to find that file. And just to help me so I can see things better, I'm going to delete this first column. You don't need to delete the first column. It's not necessary. But what we want to do is we want to look for the model that has the lowest delta AICC. And it should be the model that has the delta AICC of 0. And that is right here. So if we go across this row, we can see that this means that when we run Maxent on our data, we should use settings of linear and quadratic features only, and we should use a regularization multiplier of 0.5. Let me explain these abbreviations. L means linear features, Q means quadratic, H means hinge, P means product, and T means threshold. So when we run Maxent on our data, we're only going to allow linear and quadratic features, and we're going to use the regularization multiplier, which is a smoother for a smoothing function for more complicated models to penalize them for being too complex. We're going to use a regularization multiplier to smooth our model of 0.5. And there you have it. That is the end of our tutorial. And I hope it's provided to be useful for you.